you. lesson. For your class, because I'm still tweaking length of how long I want the lessons to be, I'm recording the lessons and posting them the traditional way that I've been doing. AS Chem I kind of have like down to I've been doing it for 12 years. This class I've taught for like 4 or 5 of the years I've been teaching because the class doesn't always there's not always enough students for the class. So I'm still working on pacing. And also sometimes students in this class, you'll find you need a little bit more time on a topic or we're moving through it faster. It just depends on our group. Some groups are stronger in certain topics than others. We may take a while on redox, for example. And so that's why I said I'll recording the lessons and posting them for however far we get on each day. I want to bring up schedule-wise. There's a lab next class, Monday morning lab. So there will not be...
At this time, all 9th and 10th graders, please report to the auditorium. All 9th and 10th graders, please report to the auditorium. Thank you.
I'll be posting the lesson after school today. So what I was saying is that there won't be a new lesson on Monday unless I need to finish something from today. So if we're able to get through everything today, then Monday there won't be a new lesson. But whatever I can't finish today, if we run out of time, then I will cover whatever questions are left on Monday before we do the lab. But the goal is on Monday just to do bell work and to have a lab that day. That's the big goal. With no new lesson on Monday, that means besides the lab handout, there won't be homework assigned on Monday. But there will be homework assigned today because there is a lesson today. I put it up already on Schoology and that it would be due not until next week on Tuesday night because that'll give time if we need more time to go over things on Monday for you to have that time before submitting the homework. Got it? All right. So let's go over the bell work. A lot of people didn't get this first part right. So when they say give them mathematical expression, they're literally like, hey, tell us what the formulas are. So do you think you should be memorizing those formulas, the ones that I gave in the first lesson? Yep, not probably. Yep, they have to be memorized. Cambridge is not going to give you a formula sheet with the pH formulas. So you do have to memorize the pH formulas in order to use them. And so here, this was actually what they would consider to be pretty easy marks because you just have to write down what is the formula and you get a mark for each of them correct. So the first one is negative log of H plus. And the second one is KW is actually equal to H plus times OH minus. And you could have also specified that this was equal to 10 to the negative 14 because that is the numerical value of KW standard conditions. But it's not always the value of KW, and you're going to see that in second bell work and why that's confusing. And then for calculating the pH, there's multiple ways you can go about this. What are the 2 methods you should use? So method 1, and I'm going to show you both. Method 1 of calculating the pH of this would be to take the negative log first. But in order to do that, you have to know what about this base. For me to just straight up go negative log, what do I have to know? This is a strong base. It has to be strong for you to just use the formulas like that. The strong base. So because it's a strong base, I could say the POH is negative log of 0.027. Okay, we could do that. And then what do you get from this if you use this method? For anybody who uses 1.57. And so that's the POH. But you were not asked for the POH. Cambridge doesn't even mention the POH because method 2 is the one that they'll use with the other set of formulas, which I'm going to show you. But it's not wrong if you do it this way. There's multiple ways to solve questions. But you have to memorize the formula if you use it this way. I got the POH. How do I get the pH from here? We know that pH plus, so this is first part, pH plus POH always adds up to 14. The pH scale and the POH scale, because they're the inverses of each other. And so we would have 14 minus POH is pH. You just subtract minus POH minus POH. And so we have pH equals 14 minus POH. I'm just writing the steps. 14 minus 1.57. You don't have to write all these steps, but you have to write the math you're doing. So you have to write 14 minus 1.57 and show your answer. And so the pH here would be 12.43. And that is correct, 12.43, which many of you got. What is method 2? Let's take a look at method 2, which is only using the formulas that Cambridge gives you. Well, they don't give it to you on the test, but the ones that they give in the curriculum. Where would you start if you have the OH minus concentration and you want to go to the H plus concentration? What formula would you start off with instead if you wanted to go the alternative method? Method 2 is to use 10 to the negative 14 equals H plus times OH minus. So some of you may have used this method. H plus times OH minus. And then what would we plug in for OH minus? The 0.027. So using this method, you would do 10 to the negative 14 divided by 0.027 equals H plus. Because that's dividing by the OH minus on both sides. And then you get what from this? I got 3.70 times 10 to the negative 15. And so I get 3.70 times 10 to the negative 13 is my H plus. That would be step 1. What would be step 2 if this is my H plus to get the pH? Now it's pH equals negative log of the H plus, which is 3.70 times 10 to the negative 13. And that would give us the pH of 12.43. You should have gotten the same answer either method that you had chosen to use. So with these formulas, like I said, there's multiple ways to go about it. You may or may not want to go into POH. Somebody asked, what in the world is POH? So I'm going to go back over what is that. We have a pH scale that measures what? Goes from about 0 to 14, 7 here. And what does the pH scale measure? Acidity, or the amount of actual H plus in the solution, the concentration of H plus. So the pH measures H plus. It's a measurement of H plus. So it goes from 0 to 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? Every movement of 1 on the pH scale is a movement of how much more times acidic or basic? Every movement of 1. So if I have a pH of 7 versus a pH of 6, how many more times acidic is a solution that has a pH of 6? Every movement of 1 on the pH scale is actually a movement of 10 times more or less acidic. In this case, moving this direction, it would be more acidic, meaning the concentration is 10 times more. And we went over that a little bit, and some of you were all going for this in the answer to the second question, that the H plus is 10 to the negative 7 in a neutral solution, because I went over that on Friday. But in a neutral solution, the H plus is 10 to the negative 6. 10 to the negative 7. In a pH of 6, the acid concentration is what? 10 to the negative 6. And in a pH of 0, what's the acid concentration? 10 to the 0, which is 1 molarity. So a 1 molarity strong acid, 1 molarity, has a pH of 0. pH of 0 is actually a concentration of 1. Right? So molarity relates to pH. The bigger the molarity, the lower the pH for a strong acid. And so that's why I told you all back in previous chemistry, I was like, you see a big number on the bottle, scary. If you see something like 0.01 molarity, not scary. So the numbers matter, like how big or how small the number is matters. And so the last thing I want to bring up here is, well, that's the pH scale. What's the POH scale? It's actually the opposite. So whenever the pH is 0, that means the POH would be 14. If the pH is 1, the POH is 13. Because instead of POH being the measurement of acid, POH is the measurement of base. And they're like a scale, the opposite of each other. So POH is the measurement of base. So if the pH scale goes up from 0 to 14, what happens with the POH scale? It would actually start at 14 and go back to 0. It's literally the opposite of the pH scale. Cambridge doesn't actually even bring up POH, like non-existent in the Cambridge curriculum, like textbook. But it is a quick way to go about getting the answers if you don't want to do the algebra here. It's a little bit faster of a method, so that's why we bring it up. I teach it in pre-ACE for that reason. Because it is. So it's just the measurement of the acid versus the measurement of base. All right, so let's get to the question that was a struggle. That I knew when I said it was going to be a struggle. Because although I had brought it up in Friday's lesson, not everybody was here, first of all. And second of all, we never actually solved the question with this idea. So let's take a look at it. It says, use the value of Kw to calculate H plus in pure water under standard conditions, but show you're working. So let's write that Kw formula down again. What is it? What is the Kw formula? H plus times OH minus. And the key here, so we've got water, and I saw somebody write this, I forgot who, but one of you wrote this. Water plus water makes this H3O plus and OH minus, right? Water plus water makes that. Neutral in water, which is the same thing actually that's here, because H plus and H3O plus are the same as each other, if you'll recall from Friday. If you weren't here on Friday, every time you see H plus, that could also be written as H3O plus. The strongest acid that can exist in water is H3O plus. And so, why does this matter? Why am I bringing this up? First of all, standard conditions, Kw, do we know that number? 10 to the negative 14. And I had mentioned, it's only at standard conditions actually that it's 10 to the negative 14. We change the conditions, we change the temperature or the pressure, we change the value of K, which is going to matter for part 2. I'll bring that up more in part 2. But we know in standard conditions that Kw is 10 to the negative 14. We don't know either of the H plus or the OH minus technically, besides common sense, like what we've heard in the past. But what do we know about them at a neutral pH? If it's neutral, what do we know about the acid and the base concentration? At a neutral, they're the same. They're equal to each other, right? We know that the H3O plus is equal to the OH minus. This brings the following idea. If we don't know what either of these are, technically, but we know they're the same as each other, what can we plug in for them both?
Just square root 14.
Correct. And so you would plug in x for both, because they're the same variable. They're the same thing we don't know. Kind of let it marinate. So this is x squared equals 10 to the negative 14. Oh, what's that? Take the square root. What do you get? A number that many of you wrote on your paper without justification. 10 to the negative 7. And that's where that number comes from, that the concentration is 10 to the negative 7. Because the concentration of acid is basically the same as each other. And the square root of 10 to the negative 14 is 10 to the negative 7. So in standard conditions, you would have that as your answer. Now, what happened here in part B? Uh-oh. What's going on? Is this standard? This is a hotter temperature, 50 degrees Celsius is like 140 degrees, 130, 140 degrees, like our temperature, so like really hot. So this is definitely hotter than standard. The temperature has been raised. And they tell you when the temperature has been raised, the pH actually is not 7 anymore of pure water. The pH is affected. It is now 6.64 instead of 7. Would that change your numerical work? Would that change your value of KW in half? What is the pH? If the pH changes, what else must be different? The OH minus and the H plus, right? What does pH directly relate to? So the first thing you're going to want to do is find the H plus concentration. So how do we do that? How do we find H plus if I've got the pH? So the formula is 10 to the negative pH. So you got to look at the formula sheet to see how do you find H plus. And that's going to be 10 to the negative pH is H plus. So that would be 10 to the negative 6.64 is your H plus concentration. How will this get you to a new KW? What can you do now? What's the formula for KW? Equals what? H plus times OH minus. If I'm in pure water, that means my H plus and my OH minus are the same as each other. That's what pure water means. So instead of now H plus being 10 to the negative 7, it's 10 to the negative 6.64, which means that KW would be 10 to the negative 6.64 times what? Times the same thing, right? Because they're same as each other. So if H plus is 10 to the negative 6.64, then OH minus is also 10 to the negative 6.64. And that's what you plug in your calculator. Or, if you're savvy and you recognize this is the same thing twice, you would square it, right? So it would be 10 to the negative 6.64 in your calculator. Definitely use parentheses and then raise that to the second power. Because you got the same thing twice. Equals your new KW. And this would be the answer I got. And I did check the mark scheme, so I don't trust myself at 7 a.m. in the morning. Is 5.25 times 10 to the negative 14 would be the new KW. So the purpose of this exercise was to bring up that equilibrium constants are affected by temperature, that's a big one to know. Equilibrium constants are affected by temperature. So all equilibrium constants that are given to you in the whole entire class, every K that's given to you is assuming that it's where? Every K that we give you. If I give you a K in this course, what is the assumption? Now we're at 25 degrees Celsius. And we're at regular pressure, which is 1 atmosphere. So like sea level. We're assuming that all conditions are standard when you're given a K. This question brought up, well, what if the conditions were non-standard? What would you do? What would your new K be? How would your K be affected? And you can see it's still to the negative 14, but it's no longer 1. The number in front changed. So it's still really small, but it's no longer 1. So changing the temperature will actually change the pH of the solution. All right, so that one was a little bit, there is a question in your homework like this. So I wanted to bring, it's towards the end, but I wanted to bring this up so that when you get to that, you at least have seen it before and can go back to your notes to try it. All right, so let's get started. Unit 1, part 2. Today, gotta wake up your brain, get your calculators out. We're getting into weak acids. And so what you saw a little bit in that second bell work is more or less where we're going with the math. We're going to start going back over equilibrium constants. now. So we are still in the same two objectives. I don't know if you remember from AS, but I said, if we only have a couple of objectives, that means we are spending a lot of time giving those objectives love, because usually they're the heavier math topics. And for those of you who got in the class, either last class or this class, this course, all the math is front-loaded. Like, unlike AS where the math came later, in this class, because it's a continuation course, the math is actually at the beginning, and then later on in the year, we leave the math. So by late December, we should be mainly leaving the math behind. Math is all front-loaded in the first part of the year this time. And then the other half of the year is organic. We go back into organic chemistry in the second half of the year. All right, here we go. So we're explaining the terms pH. Are we good with that? So yeah, we understand pH generally speaking. You should go and check mark as we go through, like you're good with this one now, or you need more help. Ka, we haven't really talked about at all. So I'm gonna put an X here because we haven't done that, but we're doing it today. pKa, we haven't done that yet, but we're doing it today. And Kw, how do we feel about Kw, the equilibrium constant for water? Knowing that it's 10 to the negative 14, knowing that you can use that to solve for the H plus or the OH minus. Put a check mark under it if you feel good with Kw, or an X if you know you still need to practice that more. And it says use all of these in calculations. And then it says, for the other objective, calculate the H plus. Brackets means what? Brackets mean? The specific units of your answer are molarity. Every time you see brackets in this class, it means you're actually supposed to get the molarity. So calculate the molarity of H plus and the pH for strong acids. We've done that. We've spent 2 class periods now doing that. But today we're going to do weak acids, right? We haven't done weak acids. This is today. And in the standards, notice they only ask you to do strong bases. You will not be assessed on weak bases. So you only will be assessed on weak acids. So I'm going to leave the curriculum to today. Well, this was me copying from the last lesson. We are covering weak acids today. And I'm going slow because it was the last topic that we covered in AS, and your brains were all kind of fried by then. So I know that I need to do some significant reteaching at the beginning of this class. These are the formulas. I'll probably keep these printed throughout the unit and add as we add more on. If I recall, last year we took our first test in A-level around mid-September. If I had to remember, put a date when we took our first test. So we're not close to the first test yet. But as we go through the unit, I'll keep adding what we've learned through so you have like a little handy guide as we go through each lesson. All right, here we go. What does the value of Ka tell us? So going back to pretty much equilibrium. This is where we left off. In AS Chem, we are basically to be continued. Back in AS Chem, we learned about capital K. And you were supposed to memorize a kind of formula for it. You remember what it was? It was products divided by reactants. And we would only have equilibrium if you had double arrow in your chemical reaction, meaning your reactants were turning into products, and some products were going back to reactants. So if I had this, for example, right, A goes to B plus C, then my formula would be, or my expression would be what? It would actually be B to the first, because there's a 1 in front, times C to the first, right? Because there's a 1, and a 1. A B to the first. Do we have to write 1?
No.
There ones? But if it was a 2, I would need to write it. And then on the bottom we would have A. And this is generally how equilibrium expressions work. Always products over reactants. And if you have multiple of your products, you multiply them. And if you have multiple reactants, you also multiply them. That is generally how the equilibrium works. Now, you will have to understand K's numerically, meaning what if you had a K that was 10,000? What does that tell us about the amount of products versus the amount of reactants? What do you have more of? Yes. If I have a K of 10,000, this indicates more products by a large amount. And what if K was 0.0000002? What would that tell us? More reactants. So I'm giving you this idea because we need to go somewhere with this. More reactants.
Wait, so if it's greater than 1?
If it's greater than 1, favors products. If it's less than 1, favors reactants. That is where I'm going with this. But that idea is because the formula works out like this, the bigger the K, that means the bigger the number on the top you have is, which means the more you have of products. Whereas if I have a bigger number on the bottom, that means I'm going to have a number less than 1, and it means I have more reactants at the end of that equilibrium. So that tells us, and I'm pretty sure I brought it up. I just know I went really fast at the end of the year, so that's why I'm going slow now. If K is more than 1, that tells me something. What does that specifically tell me? More products. So if I see any K value that's more than 1, I have more products. Yes, more products. If K is equal to 1, this actually means you have same amounts, right? The top and the bottom is the same. And if K is less than 1, more reactants. So there's actually a lot of marks on A-level exams by just looking at numbers of Ks, whatever the K is. And if they give you a big K, you're like, oh yeah, makes more of the product. And little K makes the reactant, goes to reactants. There's actually, on an A-level exam, there could be 4 to 5 points out of 100 points just on this one little concept that we will be revisiting over and over and over again throughout the year. So that's why this is a good place to start. So yeah, we will be working with equilibrium in the first half of the year a decent amount, starting with this chapter. Are we good with this so far? The ideas? Okay, so Ka. What K is that for? You're going to have a lot of Ks, and they're all going to be products over reactants. Every single one of them is going to be products over reactants. But when we talk about Ka, they give you a Ka. That means that it's the constant for a weak acid. So it's the constant, equilibrium constant for a weak acid. So Ka is the equilibrium constant for a weak acid. And one more thing before we move forward. We just said this. Didn't we learn a K already in the first initial lesson, Kw? What was Kw at standard temperature and pressure again? 10 to the negative 14, right? And that was for the reaction of water and water. That's the reaction of water and water, right? The auto-ionization of water is the fancy words for this. So what does Kw tell you? 10 to the negative 14 about the reaction of water with water. What does 10 to the negative 14 mean? 0.000, like there's a lot of zeros there before you get to 1. 13 of them, and then 1. What does that tell you about the amount of products versus reactants in the ionization of water? There's way more reactants, right? It means a very small amount has broken apart. Very small amount actually ionizes. That's what this number is supposed to communicate to you. So the smaller the K, the smaller the amount of products. The bigger the K, the bigger the amount of products. That in general needs to hold true throughout what we learned this year. All right, so I wrote this. The larger the value of Ka, then, would it make sense, the bigger the number of K, the stronger the acid? Bigger K means more product. Acids break apart H+. So bigger K means more right? So the bigger the value of Ka, the stronger the acid you're going to have is when you're comparing weak acids. And we're about to get to this very shortly. I just wanted to give like a big intro to this. Are you supposed to memorize your strong acids and strong bases? I'm going to write them down one time on the next slide. You're supposed to memorize your strong acids and your strong bases. And then anything that's not strong, you just assume is weak. That's the idea. So what are the strong acids that Cambridge wants us to know? This is more than enough. Like, there were only 3 of these that Cambridge needs you to know, but this is a whole list of your strong acids that actually exist. What are the 3 that Cambridge wants us to know? You could just circle them.
HCl.
HCl,
Sulfuric acid.
sulfuric acid, and nitric acid. These are the 3 that are required to be memorized. They're the same ones I've been saying for 2 years. Like the same 3 acids I've been saying for a few years now. There are others that exist. HBr and HI. Actually, down that whole group 7 except for HF is a strong acid. If I got a lot of oxygens on my halogen oxyacids, then I actually also, those are very strong acids as well. So there's actually more strong acids than what Cambridge needs you to know, but we try to keep it to what Cambridge needs you to know. I won't test you on the other acids. So required to be memorized. And what are the strong bases, just to recall? And there, Alex, if you want to make sure to write these down because you need this for the first lesson. The strong bases are all the hydroxides from group 1. From group 1. And just a couple from group 2, right? So it would be LiAOH, NaOH, KOH, RbOH. You write it enough times, you just start to memorize it. CSOH, and then for group 2 starts at strontium. SROH2 and BaOH2 are the only 2 strong bases in group 2 you need to know. Those are all the strong bases. BA? That area of hydroxide.
What's HF not?
That's a good question. It's coming up in the lesson. That is actually, there's a whole slide for HF later on. It is interesting because HCl, strong. HBr, strong. HI, strong. HF, you would think, because fluorine's the most electronegative element and hydrogen has a much lower electronegativity, you would think it would be strong. But it's not. It's actually a weak acid by definition. So that's, we're going to get to that in a little bit, like why that can be. Experimentally, it has a Ka. If it has a Ka, that means it doesn't dissociate completely. All right, so strong acids look like this, single arrow. Strong acids have no equilibrium. So you may want to write that underneath. If I've got a strong acid, you should not be setting up an equilibrium. You should not be doing products over reactants. You should just be plugging straight in the pH formula. Yes? Weak acids have an equilibrium. What does that mean? That means that not every HF that breaks up turns into H+, and that should actually be a F-. I don't know. That's not been corrected, but you should correct that to F-. If I have HF, I'll see double arrows, because it's weak, and I'll have some H+, but not every HF converts to H+ in the reaction. Some goes back to HF, which means you have equilibrium in a weak acid. There's some formulas here that are coming up that you're going to need to be aware of. So if you have your formula sheet from a couple days ago, the cardstock, you may want to take it out to add a couple formulas to it so you can, so you can keep track along so you don't have to keep flipping pages. If you don't have a cardstock, I will give you one, just so you keep your formulas in one place. It's helpful. You want to, right? Okay, I can get you a Sharpie, yes. The back I had just done like acid-based ideas on, but the one side is the summary of the book. I will bring you Sharpies. I had tucked them away, but I'll bring them out. Well, Sharpie? I have one. Any? Okay. So, two formulas that you will need to know that we're going to use in today's lesson. And I actually should change X to A, so I'm going to do that right now before we move on. And you can do that in your notes. Because I was looking at some questions, and instead of using the letter X, Cambridge uses the letter A. So I'm going to use it. Doesn't matter. But the idea is that you have an acid, so that's why they're using the letter A from current slide. So you can change it to this. Ka is defined as H plus times A minus over HA. And I'm going to say, what exactly does that mean? And then pKa. Remember how pH was negative log of H plus? Remember how POH was negative log of OH minus? Whenever you have a little p in front, that just means to take the negative log of whatever that thing is. So pKa would be negative log of the Ka. So this is a formula. So these are formulas for weak acids. So you should write these two on your formula sheet.
I have no idea.
For what? A means acid. A means acid, generally. You see the letter A stands for acid. Also acid. No.
Acid times acid.
We're going to go over what this is in a short second.
That's a negative acid.
What? It's the conjugate base of the acid. Those words. So actually, this formula, if you know how equilibrium expressions work, you don't have to memorize this because you can come up with it on your own. Because it's just products over reactants. So this is the equilibrium expression. So if you know equilibrium expressions, the equilibrium expression for a weak acid is always going to be like this. And I'm going to teach you how we get that very shortly. And then this, if you know how pH formulas work, you can pick this one up real quick too, because I had just mentioned pH is negative log of H. POH is negative log of OH. pKa is negative log of Ka. So anytime you see a little p in the front, it just means measurement of that thing, take the negative log of it. So that way you're not like memorizing a billion formulas, you're memorizing the idea. P means take the negative log of whatever it is. pKa, negative log of Ka. So before we move forward, I had added this slide in as I was revising last night. You should get comfortable with writing equilibrium expressions or reacquaint yourself with writing equilibrium expressions. This is a checkup from the new textbook. Write equilibrium expressions for the following reactions. What would you do here? What is the equilibrium expression again? K equals products over reactants. But we have to put the exact products we have and the exact reactant we have. So what are the products we have here? So you put H plus in brackets. Why do we use brackets? Let's remind ourselves. Why brackets? Molarity. Because everything here is dissolved in water. Because dissolved in water or aqueous, that means water, right? We're using solutions. Solutions are concentrations. Concentrations are molarities. We use brackets. That's why we have to use brackets to state what's going on. So H plus is my first product. You don't write the state in your equilibrium expression, you just write the identity of what this is. And what's my other product? That thing. Do we need to know what that thing is right now? No, we just have to match that thing. That is this is benzoic acid, but we're not there. Minus, like that. Products. And then what's my reactant? This. Benzoic acid. So what does this reaction describe? What is this reaction describing to us? Benzoic acid is breaking up its H plus, right? The acid is coming off into solution. Does every H plus in benzoic acid break off? No. Only some breaks off and some stays with benzoic acid, which is why we need this. That's why we need that formula, because we have to figure out how much. This is this. Would you agree?
What? Yeah.
This is that. They're the same thing. It is the same formula. This is a general formula that works for every single weak acid equilibrium, because every single weak acid breaks off one H plus. So it's going to work the same way every single time. Let's try it again. This one. Come up with the equilibrium expression. K equals products over reactants, right? First product is H plus. Second product is CO3, 2 minus. And then what goes on the bottom? What's on the bottom now? This. What's this? HCO3 minus. That's it. Is this also the same as what you saw here? It is. So this is a general formula that works every time you have a weak acid. But if you know how equilibrium works, it's technically not something new you would need to memorize, because it's always products over reactants every single time. What type of K is this? Because notice I left out the type of K, but you should fill it in. It's called K. It is KC technically, because it's a concentration. But because it's a weak acid, we can also call it a K. A. So how it would be printed to you in a question is Ka. We provide you the Ka, which means the constant for the acid. Yes? Good with this? All right. So, can you write a chemical reaction? For dissociation, what does dissociation mean? Break apart into ions. For each of the following monoprotic acids, hydrochloric acid, can you show its chemical reaction that breaks it apart? How would you do it? You first have to know what hydrochloric acid is, which is HCl. Should you include states?
Yes.
Aqueous. Single arrow or double arrow?
Double arrow. Yeah, it's a
Single arrow.
Of course.
Strong acid. Will Cambridge tell you if you have a strong or weak acid? That's going to be an on-you decision to make. That's why I told you what you have to know. Hydrochloric, nitric, sulfuric. What are my products?
H. CL.
States?
Aqueous.
Perfect. Ammonium ion. Uh-oh. Do you remember ammonium? You're literally looking at where the polyatomic ions were sitting last year. They're not there right now. NH4
It's this association, so you need to pick one.
positive charge. NH4 with a positive charge. That's ammonium. You need to break off a H plus because it's a dissociation, right? So what would your products be?
This is weak.
It's weak because it's not one of the three strong acids. It's weak. So you get double arrows. So what are your products? H plus and NH3. Because it's positively one charge, but you're taking off the plus one. So it should now be neutral. This is that idea that the charges have to match on both sides. If this is positive one, then the addition of these two should also be positive one. Your charge should be
the one.
because it's a weak acid. Because it's not the three that you were told to memorize. And I mean, these are all the strong acids. It's not one of these. Basically,
So it's gonna be weak,
it has to be weak.
but it's, you just assume it's weak.
Assume it's weak
Unless
if
it's
it's those three that you were told to memorize. And then last one, chlorous acid. This is also going to be weak because it's not HCl, it's not HNO3, it's not H2SO4. Chlorous acid. HClO2 goes to single or double arrows? Double arrows. And then what are our products? H plus breaks off. And then what does the other product have to be? Remember, this overall charge was 0. So the overall charge of both of these has to equal 0. So if H plus is positive 1, then ClO2 has to be negative 1. And I have mentioned that, but not everybody was here, so I'm repeating myself. Charges will get you in trouble. Charges will get you in trouble. If you wrote H plus ClO2, although, yeah, you broke it apart, because you didn't write the charges, Cambridge is going to not give you the answer. They're going to say you don't get that mark because you didn't understand that it's H plus 1 and ClO2 minus 1. So make sure that your charges always balance out. If you start with a charge of 0, you have to end with an overall charge of 0. Yes? Go ahead.
Not give us, like, you know, like something,
Mm-hmm.
just make it small and not put it in. Would they like be pissy about it, or
I'd have to see what you wrote. And I'll give you more advice when you write it down in your work and show me. Okay, I've talked about this. Considering the following acids and their Ka values, which acid do you believe would be the strongest out of the three that we just looked at? 3 of the ones we've just looked at. Look at their K. This K value, this K value, this K value. Which one is the strongest? What is the concept with the numbers in K that we said? We said the bigger the K, you may want to write this down and remind yourself. The bigger the K, the stronger the acid. Let's revisit that with one of these examples. If I have a big K, what does that mean? Big K means more products. Well, where's the H plus broke apart on? The reactant side or the product side? The acid is on the product side. So big K means more acid. More acid means stronger, right? So going back, bigger K, stronger acid. Which of these 3 acids, by definition, even though none of them are strong, which one is the strongest? It's actually the second one. And so it's HClO2. And this reasoning is because 1.2 times 10 to the negative 2 is larger than the other case. How do we know that? The bigger the negative exponent, the more zeros, right? Bigger negative, I'm going to write that down so you can remind yourself when you're studying. The bigger negative exponent indicates more zeros. Meaning it's 0.00000, like that. There's more zeros if it's a bigger negative exponent. Whereas -2 actually means this is just like 0.012. That's what that is. So if you change it into standard notation instead of scientific notation, oh my gosh. Surprise. But that's what this is. 10 to the negative 10 is that, is this very, very tiny number. So when I'm comparing K's and they're small, I look for actually the one that's closest to 0. When I'm looking at negative numbers, the smaller negative number is the bigger actual number. Just confusion. Why isn't there a Ka that exists for hydrochloric acid? That's the answer. Because it's a strong acid, there's no equilibrium. That's it. Yay. Sometimes those, that's from the textbook. This is chapter, if you do have the textbook from me, or you're following along or you want to borrow one from me, we're in chapter 21. We'll be here for a while, for at least the next 3 weeks. We're in chapter 21 in the textbook. What about pKa's? What is a pKa again? So go ahead and write this down, and I'm going to explain this more with the math in a little bit. But it actually turns out the larger the Ka you have is, the smaller the pKa number is. This is actually the same idea of pH, because pKa's work the same as pH does. So I'm going to write something else out here. The greater the amount of H plus you have, what happens to the pH again? If I have more acid, what do I expect to happen with my pH? It goes down. So you can use this idea to help you out with the same idea. It's the same idea, because greater Ka means greater H plus. That's dissociated. So the greater H plus, the lower the pH. The P is always the opposite. So the greater the Ka, the lower the pKa. Published, if you ever take organic chemistry, it's like if you want to be a doctor or a pharmacist, and you take a course in organic chemistry, you're only going to see values published as pKa's. And the reason why is the same reason in middle school you only saw pHs. You never saw H plus concentration in middle school of 0.000017 because they're like, we're not going to have middle schoolers look at that. we're not going to do that. So why would you look at pKa's? Is because the numbers are easier on the eyes. It's easier to look at. It's easier to look at a pH of 1 and say, oh man, that's a strong acid, than for someone to tell you there's a 0.1 molarity concentration of HCl. You're like, oh, that's a strong acid. I don't think in middle school you would have put that together. The same things with pKa's. All you have to look at, and this is it, organic chemists don't really do math. They don't. But once they get through their initial classes, they just don't do any more math. Pharmacists don't do any more math. They look at this for ideas. So you look at these numbers and you're like, oh, what's the strongest acid? When you're looking at the pKa's, what are you looking for? Smallest number. Smallest number is going to be strongest acid. So which of these, and these are just some random organic things, is the most acidic out of these choices? Carboxylic acid, right? The one with the smallest number, 3 to 5, is smaller than everything else. So carboxylic acid. And this is because smallest pKa value. So you can actually relate pKa as the same idea as pH. The lower the pH, the stronger the acid. The lower the pKa, also the stronger the acid. Same ideas here between pH and pKa. Lower pH, stronger acid. Lower pKa, bigger Ka, which means bigger acid. It's all interrelated. Kind of got it? So, what about HF? I did dedicate a whole slide to this because at its outset, it doesn't make sense. HF is actually, if you look it up online, it's super corrosive and it's super dangerous. And if you were to put your hand in HF, it would be a very, very bad time. Worse than hydrochloric acid. Why? HF is capable of dissolving many materials. It can react with glass. It can react with glass. Whereas all of our other acids are stored in glass. So why is it, first of all, not strong? We know because it has a Ka, by definition, because it has a Ka. That means that not every H plus is broken off. That literally means if there's a Ka published and you're given a question and they're like, the Ka for this is this, and they give you a number, that means by definition you don't have a strong acid. Ka means you've got this situation. You've got some that's broken off and some that's not. So why in the world is it so dangerous then? And why would many people think, but it is a strong acid because it is so dangerous. It dissolves many things. It reacts with your skin. What's going on with HF?
Is it because of the state?
It is aqueous. But think about the size. How small is HF compared to other acids in the category? HCl, look at the size of the atom. What is the trend for atomic size?
Downward bigger.
Down big,
That's a-
up small, right? So fluorine's the smallest ion here. So it's very small. It's a small acid. That means it can get in to a lot. That's why it'll get into your skin easier. And the reason why it's weak is actually has to do with the electronegativity because fluorine is so strong. It actually not only hogs the hydrogen, it hogs the whole thing, the hydrogen and its electron, and it takes it on itself. And that's the definition that we're given for how it works. If you want more information on HF and how it's so terrible, you can go to the CDC. It's under chemical agents for hydrofluoric acid. We do not have HF in this laboratory, just FYI.
Yeah, I think so, 'cause
Because it's so small, that's why it goes through things. That's what that word permeable
It's
is.
just the name.
Yes.
Is it in the blue box?
It's not. We don't have HF at all. No, we don't have HF. It is super highly corrosive. If I have the time, we'll see, maybe on the day we have the lab, there's a video that you can see from, I don't know if you've ever watched the old chemist YouTube videos. He's got like Einstein here. And he does like some crazy things. It's called the periodic table of videos. But he has one on HF where they use different acids to try to like dissolve chicken legs. So like to see if it dissolves skin. It exists. It's on YouTube, just FYI. They're not there. If we have the time, we'll go over it, but I still have stuff to cover in the lesson. What does it smell
It
like?
doesn't
I
say.
don't think
It
it
just says it
smells
hurts.
good. Yeah, yeah.
It says it hurts.
It just hurts. Smells like pain.
You think? Does it, I would say continuing education activity.
Anyways, all right. Textbook. We already did this. Actually, interesting. Skip. I didn't realize this question was here. We did this earlier, didn't we?
Yeah.
The textbook must have just moved it around. So if I want to calculate Ka, we're gonna get to the math now. We gotta get to the math, right? Let's see if we can get to the math. Check up 5. Calculate the value of Ka for the following weak acid. And so, do you have any idea what this is? You have no idea what this is, right? 2-amino-benzoic acid. You would not be able to write the chemical formula for that down. Are we in trouble? We're not. Because what I'm going to tell you will save your life. If you, at least in this, if you have a weak acid and you have no idea what the formula is, you use HA. What do I mean by that? We know that it's an acid, so it's got H+. We don't know what the rest is. We don't need to. We can do the math without knowing what the rest of it is. You'll learn what this is later in organic chemistry, but like, oh, yeah, it's organic. Later when you get to the benzene organic chemistry, you'll get more info on it. But as always, Cambridge likes to give you questions on stuff you haven't learned yet in earlier chapters. That's okay. That's why that formula is there that says all weak acids are HA. So, because it works for all weak acids. Works for all weak acids. And so what do I mean by HA? Well, first let me show you the equilibrium expression, and then we can create the K from there. Or you could just randomly know the formula from here. But let's do it the formal way so you get understanding of what's going on. So I got this thing. We're going to call it HA. The 2-amino benzoic acid. We're just calling that HA, right? What happens when I put it in water? It dissociates. So put AQ. We know it's weak because they're asking us for a Ka. They would not ask us for a Ka if it was not weak. So what are my products? H plus and A minus. So far following me? So what's my formula to solve for K? So the first thing to do is set up the equation. Chemical equation is what I mean. And the second thing is the equilibrium expression. Equilibrium expression. And what is that? Products over? Yeah. So we know the K and it's Ka would be these products over that reactant. So it's going to be H plus times A minus, which is also that formula I gave you, over HA. How will we solve for Ka? Put our thinking cap on. We've got now the formula. It's a formula. Go ahead, Alex.
Would you put 0.0 there? That's HA.
Perfect. Absolutely. That's a great starting point. So recognizing that if we called this HA, then this concentration is of HA. Or does that register with everybody? So we know that 0.02 equals the concentration of HA. We have that information given to us in the question. We're trying to solve for Ka, which means we have to have everything else because, you know, we're not in multivariable calculus here. We just use algebra. So we have to have everything else. What else do we have information for? Oh, we have the pH, don't we?
Yeah.
There's a number there for pH. What is that directly to pH plus. So we're going to want to, so I'm going to put 3 here where my number pH is. I'm going to want to change pH to H plus. And we need that formula. What's that formula? 10 to the negative pH, which means 10 to the negative 4.3. You don't have to write the formula down every time. You just have to show the work of you plugging the number into the formula. And so what does that give us? And I did this last night. I hope I did it. That sounds right. Let me double check on my calculator. 10 to the negative 4.3. My way too big could not be submitted on a Cambridge exam calculator. H plus equals 5.01 times 10 to the negative 5. Following me still? So I've got this. I'm just going to put a little check mark here. I know what I have to put here. And I know what I have to put here. What about A minus? Is it X though?
Isn't HA just, wait,
HA is this. 0.02 goes at the bottom. This is H plus.
wait,
Think
is
about what's going on here.
Is HA just both of
A, but wait.
It's not OH minus. No.
what's the relationship between HA?
That's what we're going to go over right now. So this is equilibrium, right? You're going to love what I say next. We learned something called ICE a long time ago, ICE tables. And in ICE tables, there was something that I'm going to bring up. You don't have to write all this down, but I'm going to give you a statement afterwards. I'll erase it afterwards. But if we start off with none of these, we start off with 0 before this has broken apart, like that's initial, then what would the change be? Plus x, plus 1x, right? Because there's a 1 in front of here and a 1 in front of here. This is plus x and plus x. Following me still? So your products would each be x. Why am I telling you this? For you to connect that the H plus amount is the same as the A minus amount. Does that kind of make sense here? However much much H plus is being made, that's how much A minus is also being made. So you may want to write that for yourself. The H plus is going to equal the A minus. So what does that mean? I'm going to erase the X table because I need that space. And so what does that mean? Do we already have the H plus?
Yes.
So do we have everything we need?
Yes.
So finally, we're going to solve. So I have step 4, solve. Plug in. We're solving for Ka. So Ka equals, what did we say the H plus was? And if A minus is the same thing, what can I do? It means I'm multiplying it by itself, right? Or I could just square it if I know how to do that in the calculator, right? And then on the bottom, what do I have? 0.02. And so it's just do the math at this point. So 5.01 times 10 to the negative 5. Multiply that by another 5.01 times 10 to the negative 5, or square it. I'm going to do one step at a time, so I'm just doing the top part now. When I do that, I get 2.51 times 10 to the negative 9, if you're following along with every step. And then divide that by 0.02 for your final answer, which is, oh my God, there's another 2.5. It actually runs to 2.6 though. But in the calculator, it shows 2.5. You're gonna like be sleeping at night and just start seeing numbers 25. This is not intentional, I promise you. And then there's actually, you don't have to worry about the unit here. 1.26 times 10 to the negative 7. Which it should be moles via minus 3, but we're not going to stress that quite yet. All right, breathe in, breathe out. You've done your first equilibrium question. Feeling okay. Shake off the cobwebs. We're going to do another one. Shaking off the cobwebs. Check up 5. Yeah, I gave extra space, but it didn't like great. So you just use it where you want. Okay, calculate the value of Ka for the following acids. So can we go through this process again? Can you try it this time? I'll give you about 5 minutes and I'll check it. It's the same exact thing. It's the second example. So 5 minutes. Go ahead and try it. I'll check it. And if you have it right, you get a sample. Is 5 minutes enough time? No? Okay. I'm going to put 6 for now, and then we'll revisit in a few. Why do you say maybe when you already have the answer?
Where? 1.26. Is this right? I don't think so.
Did you know
Oh, yeah.
it's funny?
But now I'm done.
This one, not that one. That's your final answer? This is right. So check to see what was done. Julio, that was fast. Oh, that's why I didn't. Let's check.
Do you love my work? Oh, so you have the right answer?
I don't understand your words. How did you? Oh, pH. I did the wrong thing. Okay, yeah. I'm stupid.
Perfect. All right, as you get the answer, make sure you're checking through and seeing that you can try it. You're on your own question now to do. I'm going to set it to about 2 more minutes. 2 to 3 more minutes for those of you still working. Did you algorithm that? What? use the algorithm to solve?
It is.
Technically, you just didn't show
Oh,
like
you just-
all the stuff.
I just put it all in the
You
calculator.
just put the final formula in the calculator. Yeah, that's actually what I did to get these. But because I know the formula in my head.
Cheater.
I would have squared it, I would have gotten it right. So what did you get?
We are on our path.
1.26
All right. Couple more still waiting for. We still got 2 more minutes before we continue. We're feeling. Like Sophia says what everybody's feeling. In general. She's like 172 days more left of school. Why do you do that?
Okay, I'm done. I did it. I caught up. I'm amazing. I know. I know. Okay, I'm a. I want to.
If you send it to oh yeah, 333-962 at baseschools.net now. They took those away from us. Just let them know.
Because H and H.
Do you have to?
Just square.
There's something.
That, yeah.
Wait, this should be your final answer.
They're in a different.
Put a box around it. Yeah,
Oh,
this
so
should be your
every
final
other
answer.
day.
That was your work? Just put a box around your final answer so it's over here. All right, over here. You ready? Working it through? Okay. Let me know. Ready?
Not me.
Correct.
At least that's what people call it. I say it's not.
All right, it is time to move on. Damani just showed me later on. If you did get the correct answer, you got 1.26 times 10 to the negative 5. And I can tell you I have had students in the past, students that have been successful in A-level chemistry, that their decision was they were like, I'm not going to memorize the equilibrium. I'm just going to do HA is, or sorry, KA is X squared over HA. And just knowing that X is H plus. I've had students do that before. If you want, that is like the hacks way to solve any weak acid equilibrium question. So this is the life hack way. Where you just have to know X is H plus. And it always works if you have a weak acid. Right? That's what many of you just went to do. You just plugged in that formula. All right, so I had already brought up what this formula was. It's negative log Ka, it's pKa. We're gonna do a couple questions about this now. Log 10 just means that's the base, but that's the automatic base in your calculator, so you don't have to stress it. If you have the Ka, you take the negative log of it, you get the pKa. So calculate the pKa's for each of those questions that we did. 1 and 2. I think one, was it 1.26 times 10 to the negative 10? 5A1 and 5A2. Let me see.
4.9 for the second one. First one.
I think I had done a Ka of 1.26 times 10 to the negative 7 here. And a Ka of 1.26 times 10 to the negative 5 here.
Oh.
So what would the pKa for the first one be? Was it 2.8? It's rounding. Don't stress it. Put in the 2.8. It's fine. For what? Negative log? So for 581, it would be negative log of 1.26 times 10 to the negative 7. I get 6.90. Tell me if you agree with me. Yeah, that's with the rounding. And the other one I got is negative log of 1.26 times 10 to the negative 5. I get 4.90. That's it. Good with this? We can calculate pKa from Ka. Something to note. Which of these Kas was smaller? The first or the second? The first was smaller. And the second was larger. The larger one has the lower pKa. Remember we said that? The larger the Ka, just to repeat that, the lower the pKa, which also means the stronger the acid. So these are the factors that give you stronger acid. All right. Are you ready for some Cambridge questions before we go for the day? So everything we've done has been from the textbook, right? But we know the textbook is easier than like the actual papers. If you go through the textbook and you look at the questions, you're like, these are easier. And so that's why in the lessons I always integrate Cambridge questions so we can see what do the actual questions from Cambridge look like for us. So here we go. First one. And this is, some of this is from an earlier lesson, not all of it's from today. What is the definition? And you don't have to write it down yet, you may want to wait for me. What is the definition of a conjugate acid-base pair? So knowing that, like for example, H-bro is an acid, and bro minus is a conjugate base of that acid. These two are considered a pair, the H-bro and the bro minus. So what's the pair? And the definition is actually much easier than you think it is.
The acid that turns into a base.
The pair is when you have a species that differs from 1H plus, or a substance that differs by 1H plus. A substance that differs by 1H plus, meaning you've got the acid version on one side and the base version on the other. That's actually the mark scheme definition, a substance that differs by 1H plus. You've got one more H plus on one side than you have on the other. So that's the first one. Next one. What are the pairs here? You get a mark if you can identify. I gave you one, didn't I? I have H-bro and bro minus. What's the other pair? What order do I have to write them in though?
Oh, H3O plus H2O.
Yeah. So the way they tried to get you here is specify the acid comes first and the base comes second. And in the second pair, H2O and H3O plus, isn't this one the acid version? And this one is the base version? Make sense? Is that Peter? I can tell his voice. Welcome back. You're just in time for the Cambridge questions. All right, and now we're gonna get to the spicy stuff. As soon as he walked in. Sorry. Calculate the pH. Show you're working. Okay, so let's walk back. This is part of the same question. X is a solution of H-bro. H-bro contains 4 times 10 to the negative 3 moles of H-bro. in 100 centimeters cubed of solution. That's numbers, right? Numbers we will care about. They also give us it's a weak acid. They want us to get to the pH. So first of all, where do you think we may want to start in this process? Knowing it's a weak acid, we know we're going to have to use that formula, right? Find the concentration. So I'm going to write that on the next slide. So I would say that step one here would be to change units to molarity, right? So change units to molarity, which is moles over dm cubed, right? Moles over dm cubed. So how will we do that? Change units to concentration. Concentration is moles over dm cubed. So go back to here. We have the moles. Do we have the dm cubed? No. Do you remember what to do to change cm cubed to dm cubed? Remember, cm cubed to dm cubed actually means move your decimal back 3 spaces. It's always move decimal to the left 3 spaces. Why? Justify for Alex, because I explained it on a different class period. When we go back to King Henry died unusually drinking chocolate milk, like that process, K, H, D, A, U, D, C, and M. If you'll recall, if we're going from centi to deci, we move over once. But because it's cubed, we have to do it 3 times. Do you remember that? So that's the idea. You have to move left 3 spaces to go from centimeters cubed to decimeters cubed, which means that instead of writing 100 centimeters cubed of solution, you would write 0.1 decimeters cubed. Are we okay with that? So then we're going to start by doing 4 times 10 to the negative 3 divided by, yeah? 4 times 10 to the negative 3 moles? 0.100. And this is H bro, right?
So the answer, my answer is point.
I get 0.04. Okay. So we have that. Let's go back to what are we being asked for? We have Ka. We have H bro. What's H bro? A weak acid, which means in our formula it would be HA, right? So H bro is a weak acid, which means it stands for HA. That's the HA in the formula. Yes? So then the next thing, going to the formula, what's that formula again? Ka equals, if we follow the whole thing, it would be H plus times A minus, which is the conjugate base, divided by HA. We know at this point we have HA, that's this. We found the molarity to put that. The question also gave us the Ka, didn't it? They gave us this. If we look in the back slide, it's right there. 2 times 10 to the negative 9. What don't we have? But we know they're the same as each other. So we're going to fill in 2 times 10 to the negative 9 here. Remember that x equals both h plus and a minus if you don't have a value for them. So you just call it x squared. So it'd be 2 times 10 to the negative 9, and then it's x squared over 0.04. And then we have to math it. How do we math this?
You multiply to 1.
And then we get times 0.04. I get 8 times 10 to the negative 11 equals
Yeah, then you square root it.
x squared. But I need x. So what comes next? Take the square root. What does that equal?
8.
What is that? What is that? What is that? What is
Oh, that's
this?
H plus. You have to log it, negative
That's
log that.
X, which is H plus, right? What is the question asking for? So what do I have to do now? So if X is H plus, and I need pH, what is the next step? So step 1 was to change units. Step 2, to be clear, was to solve. And then once I have H plus, step 3 is to change to pH, which means take the negative log. So it's going to be pH equals negative log of 8.94 times 10 to the negative 6. And if you get it right, you get 5.05. And that is the answer in the mark scheme. So make sure you have it. Take a picture of it if you need to.
You use 3, always 3 unless they have
3
one.
unless otherwise specified.
Like if they have 4, then you can do 4.
We are one slide from being done. I'm going to pause for just a little bit if you needed to take a picture or finish writing. I'll give you a minute. If you're ready to solve that last one on your own, you feel good about it, you can eat into it. Just one more question. You said you. I was going to help you with the first part. I'm gonna wait just a little bit. If you want to do the last question, if you want to start working on it, you can work in advance with me. There's one more question in today's lesson. One more Cambridge question. And then I'll solve it in a few minutes. If you want to try the last question while I'm waiting.
Equations are actually work, so.
How is it?
Equilibrium. So it's right.
Good information?
Yeah, but mostly.
Give me.
Fine, it depends on a lot of things, but I'm not sure. Living on stage.
Oh, yeah.
You don't need stage.
You've been here for your,
My other answer.
you know how things work. That's why I don't do a day of like how school works in ACE. I do that only in pre-ACE. Like rules and regulations, I'm like, yeah. Let's get to solving problems. Yeah. Absolutely, very good. One mark.
H plus, and then like. the
2 more marks
bracket,
available.
bracket, CH, 3.
Yeah.
Over
Never mind.
the whole thing, CH, 3. No, it's products over reactants.
All right, I'm giving you some time because some of you are working on that last question. I'll give you some time to try it first and we'll go over it in about 3 minutes.
H plus, CH3.
Equation not the expression. So this is correct for the equilibrium expression. So equation, when they say equation, it's chemical equation. It takes too long to they want reactants and products. Oh, so this will be my yes. And then this you would use for that. Yeah.
Yep, this seems right. I'm supposed for the answer. Miss, is this right? This is what they want from the equation, or do they want the actual equation?
They want the chemical equation.
I told you. I wrote it down. I trusted you.
So when it says this means chemical equation. And they also give you one line, so like
Yeah. Can you, okay, well then you should have told me that you were right, okay? Instead of just agreeing with me blindly.
Not blindly. I did.
Ah,
I
some
did.
people
I did
like
argue.
others.
that's a All right, so I'm gonna go ahead and start solving it so that we can be done. So you can check back if you're still working on it and see if it matches. For the chemical equation, they want reactants and products. They didn't say chemical equation, unfortunately, but that's the assumption. When they say equation and they give you this is added to water, they want you to do the chemical reaction. So what is that? CH3, CH, Cl, COOH plus water. They told you this is an acid, right? So if you remember from the first lesson, if you were here for the first lesson, we talked about how acids behave. How do acids behave? They donate their H plus, one H plus at a time. So which hydrogen breaks off? Always the one from the carboxylic acid. So this is the one that breaks off. And you would donate that to water. And so you would get CH3, CH, Cl, COO minus plus H3O plus. Now I know I told people that didn't have this exact thing that they also had it correct because there's an alternative answer. You could have, instead of writing H3O plus, you could have written H plus. And so the alternative method would have been to do, I'm just going to write alternative. Alt would be CH3, CH, Cl, COOH, and then just knowing, hey, that's aqueous, it's in water, its H plus breaks off, and it would be CH3, CH, Cl, COO minus plus H plus. These two are the same exact equations. One is just showing the water and the other one is not showing the water. So whichever one of these is correct. This one or the one up here. Do I need states of matter if they don't tell me that I need to give them? No, it's not part of the point if they don't tell me to give them. You don't have to worry about it. Math. What's the math to do here?
You gotta change.
So there's a lot of conversion stuff to do here, right? A lot of conversions. First, before you can get to pKa, what do you have to have? Ka. Ka, right?
Oh, you gotta do long.
So you need Ka equals H plus times A minus over HA. What's HA this time? This, right? It saves you time, effort, and pain just to write HA instead of writing the whole entire chemical formula every single time because it's a lot of letters. So you just write HA. That's that. And so what do we have to do with HA though? I don't right now have the concentration. What do I got to do? I need to find concentration of HA. And how do I do that? Moles over dm cubed. So concentration is 0.150 divided by 0.250. What do we get from that? I get 0.6. Let me know if you get 0.6. For concentration.
Oh,
You didn't do that?
no, I just plugged in the entire thing.
Well, look at it.
Basically.
What is the other thing we need from here? pH. What does the pH give us? It gives us the H plus, and it gives us the A minus, because they're the same as each other for all weak acids. So the next thing I'm going to want to do is change pH to H plus, which is just 10 to the negative 1.51. 10 to the negative 1.51 is, I get 0.0309. And that also equals A minus, right? Because these two are always the same as each other. So now what? I've got everything I can plug in. The next step is to solve for Ka. 3 is solve. So we got Ka equals 0.0309 twice, or squared, over HA, which is 0.6. 0.6. And then I get KA when I did it was 0.00159. See if you agree. I got this for my KA.
Can I write?
Oh,
So
yeah.
HA is just the
That's the
concentration.
Which one?
HA is just the concentration.
Concentration of this thing.
So it's the molarity of
So it's the
that.
molarity of this thing. So we had to find the molarity of that to put in here. Yes? And then this we get from the pH. Now we've got the Ka, but do we have the answer? We still have to take the, so Ka has to go to pKa, which means take the negative log of it. pKa equals negative log 0.00159. Is there an issue?
No, that's about the same answer. I put it all in.
And I take negative log of the answer. And I got 2.80, which I did check, and that is what the mark scheme had. 2.80.
Well, the calculators. Use a calculator.
2.80 was the answer here. 2 marks.
Do you need a zero?
3 significant figures. 3 significant figures.
I still got it wrong.
1 out of 2.
Put a zero.
All right, so I've got your homework. Let me say a couple things real quick. Remember, the homework is not due until Tuesday night. So you have time to work on it early or to work on it later. I will not have a new lesson for you on Monday because we're doing a lab that day. And we finished everything today, so we can have a bell work on this. And then we'll have a full lab on Monday. Then homework is due Tuesday night for this lesson. There's 2 homeworks posted, one written and one from Science Geek. If you have issues with formatting, please let me know. You can email me, and I'll help you out with any formatting issues with the Science Geek work. The table of KAs I'm giving you is for the Science Geek homework, because they assume that you have a tab open to that table, but just in case you don't, I'm giving it to you. The paper one.
I told you. I told you that's what was going to happen.
And I agree with you.
I did the same thing.
Okay, well.
That's for the Science.
If it makes you feel any
You
good.
need like a table of contents for it.
I said I was gonna
Because they'll give
not
you random projects, and then I forgot to, like, you don't have to write right now.
I forgot mine at home, so I think it's right now.
Here you go.
Oh, I did get it. This as well.
Do you mind if I did? Yeah. So,
It's X squared over concentration.
you're welcome. David,
This is X squared over X squared.
homework?
That's all I ordered today.
Oh, okay, okay. And so I need for Stefan and for Alex. And it's not due till Tuesday night.
That's all I hear.
So, yeah, it's
Stop recording.